Good morning, everyone. I'm very glad to be here with you today. My name is Yaqiong. I'm from ShanghaiTech University in China. It's a pleasure to present our research on dynamic composition of quasi-static magnetic fields for array optically pumped magnetometers. In this talk, I will cover the following 5 sections. Let's start with the background. Dynamic weak magnetic field measurements are crucial in various fields, especially in biomagnetic research. And as shown in the picture on the left, we can show that the Earth's field is about 50 microtesla, while the human heart magnetic field is at tens of picotesla, while the brain magnetic signals is even weaker at tens of femtosla. And to measure these weak biomagnetic signals, we need magnetic field shielding, and we also need highly sensitive magnetometers. Currently, the most common devices for such measurements are superconducting quantum interference devices, squids, and OPMs. OPMs hold several advantages over squids, such as integrated and smaller in size. In this time, we aim to enhance the performance of surf OPM under long-term magnetic field fluctuations. And we know that the surf OPM require an almost zero magnetic field environment to operate optimally. And to achieve this, we need to do magnetic shielding, and which can be passive or active. And passive magnetic shielding can attenuate the environment magnetic field to nanotesla range, while the active composition ensures that the OPM sensors operate under optimal low field conditions before testing. But we know that the environment magnetic field during the acquisitions process is always change. So therefore, how to maintain stable operation dynamically remains a challenge. This paper process a dynamic magnetic field composition method that allows OPMs to detect weak biomagnetic fields without another sensors. Next, we will discuss the operating principle. This is a schematic diagram of our OPM. We use a laser which is tuned to 795 nanometers to pump the atom which is in the vapor cell. And the spin evolution of the atoms can be described by the block equation, which can be shown in equation 1. And then we introduce an amplitude modulation to reduce the impact of low frequency noise. And the result can be shown in equation 2. And then when the residue magnetic field along the y and z-axis directions are zero, the equation 2 can be simplified to equation 3. And then the demodulated signals detected by the photodetectors can be shown as equation 4. And we can see that when the residual magnetic field is now to zero, the equation 4 can be simplified to equation 5, and that is to say the output signal is linearly correlated to the detected magnetic field, which is in this range. And then to maintain the output signal stability, we dynamically adjust for fluctuations using Helmholtz coils. we can see in this picture, the low frequency is feedback to drive the Helmholtz coils to reduce the magnetic shield fluctuations. And the transfer function of the system can be written as equation 6, 7, and 8. And to save time, we will not describe here. And let's move to the experimental setup. In our shielding room, we use 3 orthogonal Helmholtz coils to dynamically reduce the magnetic field. And then we place 3 OPM sensors to drive these coils. And the figure A shows the diagram of our experimental setup, and figure B is the circuit diagram, and figure C is our shielding room, and figure D shows our circuit, and figure E is our OPM sensor. Our experiment begin with digitizing the output signal, and then processed by microcontroller, and then the signal is converted and amplified before being sent to the external compensation coils. Now let's discuss our result. We first test the method in a shielding chamber, and we introduce an artificial interference magnetic field along the sensitive axis of our soft OPM, and the result is shown in the figure on the left. The channel 1 shows the signal without compensation, and channel 2 is the result with compensation, and it indicates that this method effectively reduces the field fluctuations. And then we introduce magnetic fields of varying strengths along the 3 axes to qualify their effects on the sensor's output. And the output is shown in this figure. We can see that changes in the magnetic field along the sensitive axis, which is axis, have a significant impact on the sensor's output. And then we place 3 sensors in the shielding room orthogonal, and their sensitive axis was parallel to the Helmholtz coils in the shielding room. We turned on and off the compensation system, and then we recorded 2,000 second signals. The result is shown in this picture, and we can see that without compensation, which is blue line, we can see that without compensation, the residual magnetic field along vertical directions exceed our OPM operating range, and with compensation, the result is shown in the red line in this picture, and we can see that the magnetic field fluctuations can be reduced to 10 picotesla range. And this picture shows the spatial density of our soft OPM. And then we did our magnetocardiogram test to evaluate the feasibility of the system. And this is the results, and we collected 40-second magnetocardiogram data. In conclusion, this paper presents a novel approach for dynamically compensation quasi-static magnetic field in array OPMs. And this system stabilizes the environment within a shielding room without additional sensors, and successfully controlling magnetic field fluctuations down to about 1%. And for future, We will study the stability of this method for moving magnetic fields within a certain special range. That's all. Thanks for your attention.